Okay, good afternoon. So I think it's 1 o'clock, we'll get started. I'm DK Panda from Ohio State University. This is a joint presentation. My colleague Dr. Subramoni couldn't come. So the topic here is to have focus on high performance MPI and then deep learning on the OpenPOWER platform. As many of us knowing, we are in a very exciting phase in the community where not only we have HPC, but HPC is leading to big data is leading to deep learning. So we are in a more into terms of the big data like the Hadoop and Spark, how you can actually run efficiently on the OpenPOWER platform. So, that talk is at 2:15 in room 307. So, I will start with this. This is the project some of you might be already knowing. This is the Mpi project. In my group, we have been working in now for 16 years. We were the very first ones when InfiniBand came into the picture. We started the first open source MPI, and it was available in the 2002 supercomputing, and then since then we are continuously enhancing this software stack, and there are different versions, optimized versions here. I will talk a little bit about that later, but now it is being used by more than 2,800 organizations in 85 countries, and just from our like websites, you see we are almost like a 0.45 million downloads just taking place from our site. And not just the downloads, if you take a look at all these machines, even the #1 system in China, 100 petaflop machine is being driven by our stack. You can also see the 9th ranked Oak Forest Packs in Japan, 12th at TAC, 17th. So, a lot of these top 500 systems are being enabled by the software which we have developed in my group, and this is a continuous project which has been going, and we have been empowering this over a decade. And the software stack not only is available from our side, it is also available with integrated vendors from many other industry, like if you take a Red Hat or Sushi Disk or even a OpenHPC, you will see our Mpi stack being there. So, we have multiple versions here. So, there is a basic MPI version which is the Mpi 2. So, then there is an Mpi 2X which has the advanced MPI features. It also tries to provide with the PGAS, hybrid MPI PGAS kind of support, and then there is a GPU optimized version for NVIDIA GPU. So, those are the three things I will be mostly focusing today. There are also some cloud versions, energy aware versions, the mic version which has been upgraded to KNL based. We also have a lot of micro benchmark suite the entire community uses. We issue micro benchmarks. Those are the benchmarks people use for evaluating different MPI libraries. We also have an integrated network monitoring analysis tools. So, this is the kind of our release time download. As you can see, like over the years, we are in a very steady rising curve kind of thing. More and more systems are using our stack to get the best performance. So, this is the overall like the architecture of the software family. So, as I said, not only it provides MPI, but it also provides PGAS and hybrid MPI PGAS support. We support all different kind of networking technology, not only InfiniBand, which you are hearing more and more here, also iWarp, Rocky, also Omnipath, and also for all the different platforms, not only Intel Xeon. Of course, the focus here is the OpenPOWER, Xeon Phi, ARM, NVIDIA GPUs, all the systems. We try to take advantage of their features and then trying to take it through the stack to give you the best performance and scalability. So, as the OpenPOWER came into the picture, I mean of course, the community has been there with the x86 for many years, and then over the period of time we have been trying to provide more and more optimization for OpenPOWER in our stack. So, in the basic MPI support almost like 2 years back, we enabled the initial support and we continuously enhance it. The PGAS support also has been there for almost 2 years. Now, recently we have provided some very advanced collective support. I will talk about that, and also the NVIDIA GPU support, and especially with NVLink. That is the new thing which has come out with OpenPOWER with NVLink, like the Coral kind of systems. So, we have done a lot of optimization for that. So, I will also be talking about this. So, let me start with the basic MPI support, and then gradually I will move to the other ones. So, this is where I will try to show a lot of performance numbers. So, just to illustrate you like how kind of performance you can get from the system. So, here I will be comparing not only our Mpi 2, but there are like 2 other stacks in the community. Some of you might be knowing it is the OpenMPI, and the other one is the IBM Spectrum API that has been very much geared towards OpenPOWER. So, what we are trying to show, so this is like an intra node within a node, how efficiently you can do MPI communication. And as you know, like OpenPOWER has a lot of cores. So, here you can see that this is the like the green line here. Within like 2 cores intra socket, we can actually do MPI communication in 300 nanoseconds. Okay. So, that is what it tries to show, and then this is like the intra socket small message latency, this is the intra socket large message latency, they are very similar. Intra socket bandwidth, again we are able to deliver equal or better than the other stacks, and here also very large messages, we are very comparable to the other ones. These are the internode, that means from a node to node across like InfiniBand interconnect. So here we lose out a little bit. We have been continuously working on some better solutions here to have comparable performance with the other two stacks. But for large message latency or bandwidth and bidirectional bandwidth, you will see we are able to deliver equal or better than even the other two stacks. Now that is just only point to point, but that is not always sufficient, because when jobs are running, it is also many times like multi-pair communications matter. So this is a multi-pair latency. This is a part of the OSU micro benchmarks. All these numbers you yourself should also be able to reproduce. Okay, these are using the standard benchmarks. So multi-pair. So that means since we have more number of cores here and more number of cores here, in a typical application, multiple pair communication can happen at the same time. Okay. So this is what is being measured, like a multi-pair latency. So here, what we have done, like this is our old design. We have a new design. I'll be talking. This is the MIP to XP MEM solution which is coming. So again, here you can see like Spectrum MPI, OpenMPI, we're able to deliver for short messages within the node when multiple cores are talking, like 48 to 45% benefit. Here, like a 40 to 30%, 45% benefits kind of things we can give at the basic communication. So that is with respect to latency. Also for applications with large messages, the bandwidth also matters, or even the small messages, how much concurrent communications we can have. So the higher is better. So here you can see, when compared to the Spectrum MPI and OpenMPI, we are able to deliver 1.6, 1.8x, or even 1.5x, 1.2x kind of benefits we are able to give with our design. Now, especially with now multi-cores coming, if those of you are very familiar with MPI, you will see that not only we have cores, we also have a lot of threads. So when you are trying to run a job, you need to make sure that you are actually allocating the cores and threads properly to your processes. Otherwise, you will see oversubscription and you may not get the best performance. So in fact, continuously we have been working in our library, also in the community. People have been coming up with better like a binding policies. Here we had a burn scatter. Recently we have introduced like a hybrid policy with a Newman node. I'll not go into more details here, but these are all there in the user guide. But especially we have taken the Power 8 kind of architectures and introduced a model or a binding policy which is called spread. Okay. So it will try to actually make sure that the processes which are like the nearby processes are being applied to physical cores without oversubscribing, and so that you can get better performance. And these kind of new schemes not only gets used in Power 8, but also KNL, hyper-threaded Xeon kind of things. And those are like the by default. Of course, if you really want to squeeze performance and if you know the communication patterns, you can also do your explicit binding. Very advanced users do those kind of stuff. You can explicitly say, okay, this process goes to this core, this core, this core kind of things. I'll just leave it here, and then actually our user guide tells you all the details about what needs to be done. Now, those are the kind of the basic point-to-point. Now, many of you now might be knowing a lot of applications, especially in MPI and scientific applications, are the performance is determined by the performance of collectives. Okay, the collectives are like broadcast, reduce, all to all. These kind of operations take a lot of time, and if you don't optimize those libraries, then you will see your job is not running efficiently on a very large scale system. So in my group, in this MIPS project, as well as a lot of other projects, people continuously have been optimizing a lot of these collectives. So one of them is like based on a kernel module. This is called CMA. These days, actually, the CMX cross memory attach, that has been there in the default Linux kernel. So you can utilize that. Other MPI libraries use, but we have also gone one step ahead, because if you just use the CMA by default, you will see a lot of contention and the locks. So we have come up with a new generation of algorithms which avoids this kind of a link contention, and then that's what you will see here. Like this is a reduce operation, this is an all-to-all operation. This is for short messages up to 4 kilobytes, and then up to 4 kilo, and then 8 kilobytes to 1 megabytes. So again, you can see across those MPI libraries, we can deliver you like almost a factor of 5.2 or 3.6x improvement And similarly, all to all, you see factor of 3.3 or 1.2x improvement, okay, by using the libraries which we have in our design. And here also similar like a gather scatter, those are also the other kind of collectives gets used by many applications like taking data from a lot of nodes, that is gather, or you are trying to do the scatter. So then this is that is within the node I showed. Now you can actually scale. So that these are the nodes which are the multi-node numbers here we are trying to show. So now you can see like even this is an experiment, so we only did with a 4 node like ppn 20, so up to 80 processes running across 4 nodes. So here you will see like we can actually give you even a factor of 12 benefits, 1.9, 1.x, 8.5x benefit even in the very small scale system. Similar kind of benefits we see also for gather and scatter. So then there is a next generation solutions we are trying to provide, and these kind of solutions are not publicly available in a lot of other libraries. This is called an XPMEM based solution. Cray MPI has this kind of solutions, but not in any other public open source library. So we have new designs coming up. So it actually tries to do a kernel, but also it's almost like a zero copy kind of schemes, so that you can optimize the collectives much more efficiently. And so this has not been released, it will be released soon. So this is the black line is our new design which is coming up. So again here you can see that this is a MPI to all reduce with a 20 ppn 2 nodes, similar kind of stories. We can see that we can give you a factor of benefits here. Even if you go like a 3 nodes, 4 nodes, the same story goes along. So that means we are able to provide you a scalable kind of a solution. The same thing also for reduce. Here you will see that in fact sometimes even we go up to like a factor of like 5.6x improvement, and then this is for like a up to 80 processes. You can try to see like even for very large messages, 8 megabytes, 16 megabytes, and these are becoming more important. I will talk very soon because of the deep learning applications, they use very large messages. So we need to also optimize this large message size, and this is what we have been doing to give you the very good performance. So those are like the micro benchmarks, but if you see then the question is okay, what happens with applications? So here is the mini AMR performance. So this is like the new XP based collectives. So now you can see at an application level, okay, we are able to give you benefits like when a 10 process up to 60 process, 40% benefit if you use this our library with these new mechanisms. So let me then quickly move forward. So those are the basic MPI. We also provide support, as I said, for the basic PGAS. PGAS means here we can have like a this stack actually is very flexible. It has been there since 2012. It provides complete flexibility. You can use this stack to have your application written with pure MPI or pure OpenSMEM, pure UPC. You can mix and match MPI, OpenMP, OpenSMEM. You can just play around with it, any combinations to see that your application runs best on this platform. So these are the very latest number. This is from the public version of the release. These are the OpenSMEM, which is another industry consortium where they are trying to provide the SMEM standard. So you can see SMEM get and put with very low performance, very low latency. We can try to give you here like a intra node, like a 0.01, 0.1 microsecond kind of thing. So almost bare metal we can give you performance for these OpenSMEM, like here it is UPC put and get. We also support UPC++, that also we can provide. So then the broad thing is that how we can integrate these kind of things with GPUs. Okay. Now, how many of you have heard, like if you have done some GPU work, like there is a common terminology these days called CUDA aware, MPI or CUDA aware runtime. Any one of you familiar with that? Okay. So in fact, this is the term actually we introduced in my group almost 7 years back. In our classic, we had a ISC 2010 paper. So the question we asked that if anybody has done CUDA programming, most of the time, you know, like let's say you have a system like this, we have a GPU, InfiniBand, you typically do a CUDA copy to the host memory, then do MPI, and then after you do another CUDA copy. So that means the end user needs to know learn about CUDA. So we indicated that, okay, you can do a very quick programming, but it is not highly productive because the end engineers and scientists, you need to learn about CUDA, you need to know about what GPU performance, all those things. So we asked the question that can you do it in a very transparent manner. So, that means the end engineer or scientist, if you know how to do a basic MPI programming from host, that is all you need to do. You do not need to learn anything else. Just like instead of saying MPI send from host memory, you say MPI send from device buffer or MPI receive from device buffer, and then you see the animation, everything else MPI library will take care. Okay. So, that will give you the best performance and productivity. So, that is what we have been working almost for last 7 years, continuously working, like we do very close collaboration with Mellanox for InfiniBand side, of course, in this angle with NVIDIA under funding. We take the very latest and greatest from their architectures and try to deliver the performance. So, now if you take a look at these numbers, this is what like we have an optimized MAPIS to GDR library or a GPU direct RDMA library. Look at this number, 1.88 microsecond. We can actually send data from one GPU going over network, over switch adapter to the other GPU in 1.88 microsecond. Okay. In fact, I am very proud of my team who has done the design, and also there is no other MPI stack in the world which can deliver you this kind of performance. Okay. So, this stack gets very widely used in all GPU platforms. Here you can see like HUMD Blue, which is a molecular dynamics kind of applications. It gives benefits by factor of 2 kind of thing at an application. And in fact, next time you are in Europe, in Switzerland, or if you have been to Switzerland for the last 5 years, we actually really help them to have the real time weather prediction. In Switzerland, if you open up your iPhone and see the weather, we are actually delivering that using our stack. So, we have a 3-way collaboration going on between us and Switzerland Supercomputing Center and Meteo Swiss, who was their organizer from the meteorology department. So, we 3-way we do the collaboration to give you the best performance there. So, those are on the like the numbers I showed on the x86, but now you must have seen like this OpenPOWER is being now used in the 2 larger systems which are coming out, the Coral systems in the US Department of Energy. These are the Sierra kind of thing. So, these numbers are taken from similar kind of systems. Of course, this is a Power 8, the Power 9 which is just being deployed in the actual Sierra systems. They do not have the GPU direct RDMA. So, that is why the latency is higher. Once the Power 9 will have GPU direct RDMA, you will see the performance what I showed earlier. But if you see the bandwidth, so this is where we support the NVLink, see the 33.9 gigabytes per second. MPI level performance we can actually give from one GPU to the other GPU. Okay. So, we are able to exploit that kind of a feature, and then of course, internode, these are the InfiniBand EDR. So, we are able to saturate that with the 12.5 gigabytes per second. So, this is a broad like MAPIS project, like as we have been working on these, we actually not only provide some individual solution, if some of you are not familiar, over the years now we have done a lot of best practices, because this library gets widely used. So, if you are using one particular kind of an MPI application and you want to tune, of course, MPI library has so many parameters. So, we are actually, this is a community effort I just want to share. So, you can actually take a look at these, and then if you want to contribute your tuning and all those things, we can also actually add it with your credit. So, now let me move, try to finalize the deep learning part. As many of you know, the deep learning has multiple routes. The deep learning, one direction is going purely through MPI, that is what I will try to focus here. Of course, through big data also it is going on, there is also TensorFlow, those are the things we will talk in the other talk. So, broadly in the community, this is the biggest challenge which is happening, because the deep learning frameworks are using very large message exchange. So, typically MPI library has been optimized for short messages, medium messages. So, here you need to totally rethink how to optimize the large messages, that is what I showed in the first part. And then the question is how we can achieve scale up and scale out, and then people have been working on all different kinds of solutions. So, for the most of the deep learning applications use reduce, all reduce, some of them bcast. So, that is what exactly what we have done in our GPU version of the library. This is publicly available. We have optimized all these collectives and continuously we optimize, because now you see with NVLink things are becoming different, the cost model is changing, or with a Voltas you may see some little bit of difference. So, we continuously take advantage of those and then optimize. And then also here I am trying to show some comparison in the community might be knowing, saying Baidu as a Baidu all reduce. So, the question is, and then nickel too, a lot of these kind of libraries are coming up. I actually want to show some numbers here. So, if you see this is comparison with Baidu, and OpenMPI. So now you can see that we can actually give in, even this is the Baidu, this is the MapIS 2, we can give almost a factor of 10, 3.5, or even a very large message also 20% benefit. Okay. So if you use our library and then do the already use. Same thing here also happens, this is for 16 GPUs, similar kind of things you can see like a factor of 30x, 4x kind of things better using our approach. This is with Nickel 2, this is coming up. I just want to clarify, so the Nickel 2 as such also doesn't run on OpenPOWER. So these are on x86 platform. There are some library dependencies and all, so once it gets resolved, we'll be able to see the numbers on OpenPOWER. But on the x86, if you see here, we are able to even do compared to Nickel 2, for small messages we get 10x better, here 4x better kind of things compared to that. Okay. We also have not only just optimize the MPI layer, we also do a lot of co-designing. We have actually a version of Cafe called OSU Cafe. You can actually download. We released it almost 2 years back. At that time, we were able to up to scale up to 128 to 160 GPUs. Okay, currently we are actually trying to make it OpenPOWER again. There are a lot of dependencies. Today in the morning we heard a lot of these tools need to be redesigned for OpenPOWER. Then we should be able to directly run it on this. So with this, let me conclude here. As we know, like the next generation HPC systems need to be designed with a holistic view of the big data and also deep learning. You cannot just look at just the pure HPC. And OpenPOWER platform is emerging with many novel features. So I presented some of the approaches and results here from our MapIS 2 and Ideal projects, and these solutions actually enable the high performance and scalable HPC and deep learning. So as I said earlier, from my group, we have also done similar kind of things for Hadoop, Spark. Those are like the big data software stacks. So myself and Dr. Jiawi Lu, who is sitting there, will talk in at 2:15 in the room 307. With this, let me just thank all our sponsors. But more importantly, these are all my heroes. I just come and give a talk. What you are actually hearing is 17 years of work, which we are continuously working in my group. So all these people get the credit. So with this, let me stop here, and if there are any quick questions, I'll be happy to answer. Any quick questions? It is not a single thing, as I said, like if you take an MPI library, there are so many components. Okay? So what we have been doing, it's again a holistic approach. We try to make sure that each and every thing is optimized. Okay? Because when you give it to a public version, that's what we like. A lot of people all over the world use our stack, because every application has its own different communication computation pattern. So we want to make sure that all those applications get benefited. Very detailed, yes, yes. So, yes, I mean, we, as I showed, like sometimes even we are showing like a number of like a 300 nanoseconds, you know. So we operate at that level and continuously optimize, and not just the basic performance and the scalability. We have been in this community for 16 years. As I said, when I had the first software stack, InfiniBand systems were not even running on 2 nodes, 4 nodes, and now it is running 100 petaflop machines, the number one. So we have been in the community and enabling all these things over the last 17 years. Okay. Yes.
Does the OSU Cafe framework offer any like improvements for single GPU?
I think single GPU you might see some benefits, but we always like focus on the distributed thing, or even not just, you can say like a scale up. If you have multiple GPUs within the node, we provide very good support for that. Okay? Because if you just have a single GPU, then there is not any external communication is happening. So whenever communication comes, we are there to actually optimize. Any other questions? Yes, yes. It is in fact my groups. I mean, I am a part of the Ohio State, so these are all the softwares from my research group. Yes. Okay, so thank you then.